The basics of early and current rocket propulsion systems will be discussed in this presentation. We will also explore some possible future systems. The motion of a rocket is based on Newton's third law of motion, which states that whenever one body exerts a force on another, the second body exerts an equal force on the first body, but in the opposite direction. This law is often simply stated that for every action there is an equal and opposite reaction. The rocket's motion is created by using an engine that produces a strong force in the downward direction. Because of Newton's third law, this force is balanced by an equal and opposite force in the upward direction, which causes the rocket to rise and leave the Earth. There are three basic types of rocket engines currently in use. They are liquid-fueled engines, reaction motor-type engines and solid-fueled engines. The most powerful liquid-fueled engines use so-called cryogenic liquid oxidizers and fuels. These liquids are gases at normal temperatures and pressures, but are in the liquid state at very low temperatures, typically below -250 degrees Celsius. Liquid oxygen, often called LOX, is the most common oxidizer, and liquid hydrogen called LH2 is the most common fuel. The second type are called reaction motors. These engines use oxidizers and fuels that are liquid at normal temperatures, usually above 25 degrees Celsius. The third type are solid-fueled engines that use oxidizers and fuels mixed together in the solid state. Let us look at the four main features of liquid-fueled engines. The first is the use of liquid oxygen as the oxidizer. This requires low-temperature storage facilities for the liquid and extensive preparations before launch. When liquid hydrogen is used as the fuel, low-temperature storage facilities are also required. In order to avoid this problem, kerosene is sometimes used as the fuel instead of hydrogen. The engine operates when the two liquids are fed into a combustion chamber where the mixture is ignited by an electrical spark to produce combustion. This creates expanding gases that are forced through a nozzle at high speed. The engine can be turned off by shutting down the supply of liquids. This diagram shows the operation of a liquid-fueled engine. The fuel and oxidizer are contained in two separate tanks. When the pump valves are turned on, the liquids flow into the combustion chamber where the mixture is ignited. The gases produced by combustion are forced through a narrow throat, which increases the velocity of the expanding gases as they enter the nozzle and are expelled into the atmosphere. This creates the thrust needed to propel the rocket. This is a photograph of an early liquid-fueled rocket developed in Russia during the 1950s. This Saturn V liquid-fueled rocket was used to send manned spacecraft to the Moon during the 1960s and 70s.
Reaction motor-type engines use liquids, which are called hypergolic propellants. When two of these liquids are mixed, they create a very rapid chemical reaction that creates hot gases. Since the propellants are liquid at ordinary temperature, no low-temperature storage facilities are needed. Like other liquid-fueled engines, the supply of liquids can be turned off or on to control the rocket. Unlike rocket engines that use cryogenic propellants, rockets with reaction motors can be stored indefinitely and be ready to launch at a moment's notice. A reaction motor was used in the Titan II rocket that sent two-man astronaut crews into low Earth orbit in 1965 and 1966 as part of Project Gemini. The Titan II engine used nitrogen tetroxide as the oxidizer, and a fuel consisting of a mixture of hydrazine and dimethylhydrazine. The photo on the left shows reaction motor-type engines on an assembly line at Thiokol Chemical Company in the 1960s. These were called bullpup engines. They used nitric acid for the oxidizer, and aniline for the fuel. On the right, is a photo of air-to-ground missiles used in the Vietnam War. They were powered by bullpup engines. The so-called rocket belt used a different type of reaction motor-type engine. Instead of two liquids, it used just one, 90% hydrogen peroxide. This liquid was passed over a silver catalyst that causes rapid decomposition of the peroxide into a hot gaseous mixture of steam and oxygen. In solid-fueled rocket engines, the fuel and oxidizer are mixed together with a thick polymer binder that enables the propellant to be poured into a mold. This mold is designed to allow a small hole in its center. When the polymer cures, it becomes solid, allowing the propellant to conform to the shape of the rocket. The propellant is ignited electrically, near the nose of the rocket. The fuel burns from top to bottom, and from the center outwards, until all the fuel is consumed. However, unlike liquid-fueled engines, a solid-fuel engine cannot be turned off. The main advantage of solid-fueled rockets is that they can be stored indefinitely, and be ready to launch at a moment's notice. This is the feature that makes them ideal for carrying nuclear warheads to selected targets. This diagram shows how a solid-fueled rocket engine operates. The fuel is ignited at the top of the rocket just below the nose cone. The fuel burns from the center outwards. The expanding hot gases pass down the center to the throat, and out the nozzle to produce the thrust. This video shows a solid-fueled rocket being launched.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition and liftoff of Ares 1X. Testing concepts for the future of new rocket design.
One of the most important examples of a solid-fueled rocket is the Minuteman III, a long-range, intercontinental ballistic missile. It can deliver a nuclear warhead to a target that is nearly 6,000 miles away. The missile is 18 meters long and 1.7 meters in diameter. It has a mass of 36,000 kilograms or nearly 80,000 pounds. The Minuteman III can reach a maximum speed of 24,000 kilometers per hour or about 15,000 miles per hour. It can reach an altitude of more than 1,100 kilometers. That is 683 miles. The Stage 1 engine is the most powerful one in the Minuteman III missile. It was made by the Thiokol Chemical Corporation. This photo shows the Stage 1 solid propellant core that was cast from the mixture of fuel, oxidizer, and polymer binder. The Stage 1 nozzle assembly is shown in this photo. This Stage 2 engine was built by the Aerojet General Corporation. The Minuteman III is a multi-stage rocket. The assembly begins with body section number 1, which includes the first stage engine, that can produce over 200,000 pounds of thrust. The Stage 2 engine is part of body section number 2. Body section number 3 holds the third stage engine. A small section called the post-boost vehicle engine sits on top of the third stage. The guidance system, nuclear warhead, and nose cone complete the assembly. The Minuteman III is launched from an underground silo. This photo shows a Minuteman III being launched from an underground silo. The launch sequence for the Minuteman III is shown in this diagram. Once the command is given to launch by the President, the silo is opened and the missile is fired. Once in flight, the first stage burns, and separates from the rocket after about 60 seconds. The second stage ignites and burns for 2 minutes before it is released. The third stage ignites, and burns for about 3 minutes before it separates from the post-boost vehicle. The post-boost vehicle completes its burn, and re-enters the atmosphere. The warhead consists of multiple nuclear devices that are released. The multiple nuclear devices are armed, and strike their targets.
The Space Shuttle used both liquid and solid-fueled engines. 2 solid-fueled engines were used as boosters to add power during the launch. These were released once the shuttle reached a certain altitude. The main engines used liquid hydrogen and liquid oxygen. They ran for about 8.5 minutes after launch. After the solid rockets were jettisoned, the main engines provided thrust, which accelerated the shuttle from 3,000 to 17,000 miles per hour in just 6 minutes to reach orbit. They created a combined maximum thrust of more than 1.2 million pounds. As the shuttle accelerated, the main engines burned 500,000 gallons of liquid propellant provided by the large orange external fuel tank. This video shows a launch of the space shuttle.
10. Go for main engine start. 7, 6, 5, 4, 3, 2, 1. Booster ignition. And liftoff of Space Shuttle Endeavour, preparing our home in space for a larger international family.
Houston now controlling.
Houston, Endeavour, roll program.
Roger, roll, Endeavour.
Commander Chris Ferguson confirming Endeavour is rolling on course for a rendezvous with the International Space Station. Speed 1,000 miles an hour. Altitude 1 mile. Downrange distance 6.5 miles from Kennedy Space Center orbit.
In order for manned spacecraft to travel to distant planets in our solar system, future rockets must be able to travel at very high speed in order to reduce the travel time. Our nearest planet Venus is over 25 million miles away. As shown here, the other planets are also enormous average distances from Earth. The actual distances vary as the planets move around the Sun in their elliptical orbits. Plans are underway to send astronauts to Mars in the not-too-distant future. At an average distance of more than 139 million miles, the trip would take about 8 months at an average speed of 25,000 miles per hour. This was the highest speed that the Apollo 10 spacecraft achieved when it carried a crew of 3 astronauts to the Moon in 1968. This chart shows the number of days it would take for a spacecraft to travel to Mars at various speeds. In order to reduce the travel time to 1 month, the craft would need to travel at a constant speed of 200,000 miles per hour. This is 260 times the speed of sound, or Mach 260. In order to achieve higher rocket speeds, a number of concepts are being explored. Most of these are in the early stages of development. One of these is solar-powered electric propulsion. Nuclear-powered rockets are also being developed. Antimatter propulsion is also being investigated. Using an ion engine with a gas plasma appears to be the closest to becoming practical for space travel. This diagram shows a new type of ion engine developed by Ad Astra Rocket Company of Webster, Texas. It is called VASIMR, which means Variable Specific Impulse Magnetoplasma Rocket. It uses argon, xenon, or hydrogen gas injected into a tube surrounded by a magnet. A series of radio wave devices turn the cold gas into an ionized gas called a superheated plasma. The expanding magnetic field at the rocket's nozzle converts the plasma's thermal motion into a directed flow, thereby producing thrust. Solar or nuclear power will eventually be used to generate the electricity needed to operate the system. Ion engines have low thrust, but very high efficiency, so the rocket moves faster and uses much less fuel than chemical rockets once the spacecraft is beyond Earth's gravitational field. An ion engine would be used for the final stage engine to power the spacecraft as it travels between planets. This drawing is an artist's concept of a solar-powered spacecraft using 4 ion engines heading to the Moon. According to the Ad Astra Rocket Company, a trip to Mars using a rocket with these engines would take only 3 months instead of 9 months using current systems. The rocket would need to travel at over 60,000 miles per hour in order to reach Mars in 90 days. This presentation was produced as a public service to help middle school and high school science teachers develop experiments and demonstrations that can be used in their classrooms. More science experiments and demonstrations are available on the Tops of Santa Clara Valley website, www.topsofscv.org. TOPS, or Teaching Opportunities for Partners in Science, is a program aimed at stimulating greater interest in science by middle school students.